we have gotten from people like you, and especially the speakers who have come and shared their experience and knowledge with us. Now, we have also partnered with QuizKit and the International CFD Association as well. All right, so that's about QCI. You can check out quantumcomputingindia.com if you're interested in joining a community and keep learning, continuous learning per se. All right, so with that, I'm done with the QCI's introduction, and Abhishek will let us know about the next speaker.
Thank you, Sam. Thank you, Sam, for that. So, Jamie from ISCFD will give a brief introduction about what ISCFD is, and then we will start with our presentation.
Hey everyone, good evening or good afternoon, good morning, wherever you are in the world. Thanks a lot for tuning in today for this next session. It's great to see so many of you are here and joining in. So I'm from the ISCFD, the Computational Fluid Dynamics Society, and we're basically a society that aims to promote computational fluid dynamics. We do this through a series of lectures and webinars that aim to bring experts from academia and industry to share their thoughts about what's going on and to deliver some hopefully very interesting content. So I won't say too much more, but I'll put some information in the chat, and feel free to check us out on LinkedIn and Twitter, and our website is almost ready. We're undergoing some maintenance at the moment, but yeah, feel free to reach out if you have any questions about CFD or anything, and yeah, we'll be glad to talk to you more in future. Thanks very much, and enjoy the show today.
Thank you, Jamie, for that. So, coming to the last organizers, we here are the Boson Q. I'm representing.
Abhishek, you're muted.
Oops. Thank you, Sam, for that. So thank you, Jamie, for that brief introduction. And now the last organizers are Boson Q Psi. So I Abhishek Chopra, the CEO of Boson Q Psi, is here with my organizing team who have conducted this event. So a brief introduction about what Boson Q Psi is basically we are a state-of-art venture, a new young startup that has been formed um, and is based in India, who are focusing on developing a very niche field by bringing in quantum computing, which is a very disruptive technology that has just came into the landscape of technology, and multi-physics simulation, which has been leading lot of areas of like engineering and science. So together we are bringing in a very niche software. We are a software company who will be developing this. So to learn more about it, my team will put some information in the chat. Please look at it. So that is all from our end. One bookkeeping note that who all are interested in participating in our quantum winter hackathon, there will be a survey link which you would have gotten. If not, we will put it again in the chat, and please try to fill that up soon so that we can understand where the audience is coming from and we can help mentor people much better. So with that being said, let's get started. So I will now let Dr. Naveen Prakash from Corning Incorporated USA, who's our guest speaker today, will start his presentation. So first of all, welcome Naveen. Thank you for this amazing presentation that you have put up, and I'm really hoping that the audience can get a very good feel of what you have present today.
So thanks, Abhishek. And firstly, let me thank everyone for joining in. Thank you to the organizers for organizing this, and thank you for reaching out to me for this talk. And I'm really glad to be here. I'm really humbled that you thought of me as as one of the right people to talk in this quantum winter series that you have. So with that, let me start by sharing my screen. So can you see my slide?
I think so it's just coming up. Yes.
Yes, sir, we can see it.
Okay, and you can hear me clearly? No problem with the audio?
No, everything looks good. So,
Yes, I hear you.
okay.
I'm sorry.
Sorry for that. Just to get started, I would request everybody in the audience to please keep themselves muted. And if you have any questions, please put in the chat, and we can address them at the end of the talk. Thank you.
Okay, thanks. My talk is titled "Computational Solid Mechanics, Peri Dynamics, and the Need for High Performance Computing." So I'm not an expert in any of these fields. I think of myself as more of a generalist. I do like a bunch of different things, including some computational solid mechanics, Peri Dynamics, and high performance computing. So hopefully, I can kind of put some stuff together and build a story and demonstrate that there is an increasing need for high performance computing. So just to give you an outline of my talk, I'll start with just a brief introduction to myself, and then talk about what computational mechanics or computational solid mechanics means to me, and then give a short introduction to Peri Dynamics, talk a little bit about my past work and current work on Peri Dynamics, and then end with some thoughts on high performance computing and quantum computing. So the first few slides on computational mechanics. So I was told that there's going to be a wide variety of people tuning in. So I apologize in advance if the first few slides might be a little too elementary or a little too pedantic, but I thought it would be good to kind of set the stage to talk about uh, computational mechanics or multi-physics simulations, and the like. Um, so I'll start with a brief introduction to myself. I graduated with my bachelor's in mechanical engineering from Bangalore in 2010. I worked for a little while in the manufacturing sector in India. In 2011, I joined Virginia Tech for my Ph.D. in engineering mechanics, where I worked with Professor Gary Seidel, where I led the effort to build a peridynamics capability in the group, which wasn't there before. Um, and I developed a coupled parallel thermoelectromechanical peridynamics code, which we used to tackle a couple of different problems relating to nanocomposite materials and Psr Resistivity nanocomposite materials, which I'll talk a little bit more about later. I also did an internship at Los Alamos National Lab, where again I worked on some dynamic fracture simulations with Peri Dynamics. In 2017, I graduated with my PhD relating to, and finally I joined composite materials and finished my PhD, joined composite materials, which I'll talk a little bit more about later. For about a year and a half. Internship at and then finally in February of 2019, I joined Corning as a process simulation dynamic fracture simulations with Peri Dynamics. Since then, I've been at Corning. In 2017, I graduated with my PhD relating to, and finally I joined composite materials and interest, I would say, postdoc, and computational solid mechanics, Peri Dynamics. fluid flow, just as easily. So I just wanted to kind of clear up that that maybe a misconception that might exist. And in that same vein, you can derive these balance laws for many different phenomena. It might not be just talking about linear momentum. It could be balance of energy, balance of charge density, balance of species concentration, and you might know them by different names, like first law of thermodynamics or Fick's law of diffusion, charge conservation, but they all kind of amount to the same thing, which is you're talking about some stuff which is changing in space and time. And using these equations, what you're trying to express is the rate of change of this stuff is balanced by the gradient of some flux quantity, which is related to this stuff that you're talking about. And this stuff could be, displacement or temperature or species concentration, energy, anything. So in the end, you're trying to express this concept using some differential equations, partial differential equations, and you're using a numerical method to solve this. So finally, what numerical methods are essentially doing is you're going from a continuum problem to a discrete problem. You're going from an infinite number of degrees of freedom to a finite number of degrees of freedom. You're going from an exact solution to an approximate solution. And so when you're talking about this, when you're talking about numerical methods, you're also talking about using software or using some kind of code that you write and you run on computers, maybe supercomputers, to get solutions to these problems. And I just found some interesting animations on Google to show what kind of problems that might be solved. So, for example, problems of biomechanics, automotive industry, some sort of impact problem, some sort of ballistic problem. So there's just too many to name. There's a wide variety of problems that we solve every day using these equations. In terms of computational solid mechanics, so all of this was just generally talking about computational mechanics. In terms of computational solid mechanics research, again, there's too many things to talk about. There's research areas which span theoretical modeling, numerical methods, materials modeling, multi-physics and multi-scale modeling, high performance computing, and there's just too many applications to go into right now. Some of the journals where you can find state-of-the-art research are GMPS, International Journal of Solids and Structures, CMAME, Engineering Fracture Mechanics, International Journal of Fracture, Journal of Computational Physics, Mathematics and Mechanics of Solids. So if you're interested in knowing more about state-of-the-art research happening in computational solid mechanics and all things related, you can find it on some of these journal publications. So moving on, I'd like to talk a little bit about Peri Dynamics. Hopefully, to people who don't know what Peri Dynamics is, I can kind of briefly introduce you to this newly developed and developing field of Peri Dynamics. And my aim with this section is to kind of demonstrate that there are other non-classical theories of continuum mechanics which are being deployed today to tackle pretty challenging problems in science and engineering. And these kind of new and unique theories and numerical methods are needed to tackle some of the most challenging problems that we have today. And hopefully I'll tie that into the need for high performance computing as well. So let me start by talking about a specific area of solid mechanics, which is the modeling of material damage and fracture. So engineering materials of various types are continue to be pushed to the limits of their performance today, and the modeling of damage, failure, and fracture of these materials remains an extremely challenging problem in science and engineering, and we need robust continuum mechanics theories and numerical methods to predict extreme material deformation. I have some examples of some disasters that happen due to our maybe inadequate understanding of materials, performance of materials. For example, the failure of O-rings at low temperature conditions in the Challenger disaster, metal fatigue, which led to failure of comet jet hulls, fracture of Liberty ships during World War II due to ductile to brittle transition in steel. So some of these problems are, historically famous or infamous for um, where materials failed and failed catastrophically. So this is just, I'm trying to drive home a point that this is a very important and challenging field within computational solid mechanics. And we have a lot of uh, uh, methods that have been developed to tackle these problems. Traditional finite element methods are great for stress analysis, but I'm not sure how good they are for modeling extreme deformation and damage and fracture of materials. They can often cause extreme deformation, can cause mesh entanglement, can lead to non-invertible matrices. Some methods which are commonly employed are continuum damage and cohesive zone models, but they can cause results to be mesh dependent. Some other methods like the element-free Galerke and extended finite elements were designed especially to avoid mesh dependence, but they can be extremely computationally intensive and complicated, especially when you're trying to model these phenomena in 3 dimensions. So with that, I'll transition into the theory of Peri Dynamics and how this might circumvent some of those problems. The theory of Peri Dynamics is about 20 years old now. It was proposed by Stuart Silling at Sandia National Labs. So it's not just a numerical method. It's a different way of looking at continuum mechanics. So the main basis of the theory is that it assumes non-locality in a continuum as opposed to just local interactions. So it assumes that infinitesimal particles near each other can interact through some forces. They don't need to be just nearest neighbors to interact. They can interact over finite distances. And what happens is this concept manifests itself as integral equations in the linear momentum equation instead of partial differential equations. So, for example, we talked about this linear momentum equation and how the internal force is represented by some divergence term of stress tensor. So instead of that, everything else remains the same except just the representation of the internal force density is now represented as an integral term instead of a differential term. So I'll just go back to that 1D example that I gave, where we talked about how this infinitesimal material is interacting with its neighbors and the rest of the material through these stresses at the left and right boundaries. So that's what you would find in classical elasticity or classical continuum mechanics. Whereas in Peri Dynamics, what Peri Dynamics proposes is that you're really talking about not just immediate neighbor interactions, but you're talking about long range interactions, right? So you have more than just nearest neighbor interactions. And when you derive in a similar way, if you derive the linear momentum equation, what you end up with is you can express this internal force in a discrete problem. You might express them as a summation of forces, and in a continuum problem, you might express them as an integral of forces. And the advantage of this is that these long range interactions don't need to be continuous. So if you have a discontinuous displacement field, right? So it becomes a problem when you put this discontinuity in when you're trying to take a derivative of a discontinuous field. Right? Derivatives aren't you can't define derivatives very well at discontinuities, but you can always you can integrate over discontinuities. So the advantage is that you can model discontinuities like cracks in solid materials with this method. And over the last several years, this Peridynamics has been applied to a wide variety of problems. For example, crystal plasticity at the microscale, fracture in oxide nuclear fuels, modeling tumor growth, geomaterial fragmentation under impulse load, splitting corrosion damage, hygrothermomechanical analysis of electronic packaging, so a lot of multi-physics, hydraulic fracturing, and so on. So there's a lot of wide variety of applications for Peridynamics. And I'll talk about a little bit about one of those applications that I worked on, which is in the area of nanocomposite Psr Resistivity, and this is in collaboration with Dr. Gary Seidel, who was my Ph.D. advisor at Virginia Tech. So we used Peri Dynamics. We also did multi-physics modeling and a little bit of multi-scale modeling, and also implemented this in a high-performance code in a parallel code. So there's a little bit of, like I mentioned before, there's a little bit of everything that went into this that went into these simulations. So the fundamental problem that we were looking at is modeling of energetic materials or explosive materials that are commonly used by, let's say, the Army Research Labs or Air Force or any kind of defense services, right? These weapons are expensive and they need predictive maintenance, they need scheduled maintenance, which again can be expensive, and they are very critical applications, right? If you don't take care of these materials, they can any kind of error can lead to a lot of loss of infrastructure. Loss could also lead to loss of human life, right? So this is a very critical application. And the question was, how can we measure accurately the structural health of such weapons under the stresses of service, transportation, handling? How can we predict the reliability of these materials, especially when they undergo like a drop in impact event, for example, let's say that they might undergo during transportation or handling. We need these materials to be reliable, and we need to know the current state of these materials. Our group at the time was heavily involved in nanocomposite materials and Psr resistivity of nanocomposite. So we thought, okay, that might be some kind of that we can apply that for this problem. So our idea was to use the piezoresistive properties of carbon nanotube nanocomposites for in situ real-time structural health monitoring of these materials. And this is in the spirit of creating a digital twin of the material. And I'm going to talk a little bit more about digital twin later in my talk. But for now, suffice it to say that a digital twin is just a real-time model or a virtual representation of some physical thing. So we wanted to, instead of using external sensors to monitor such a material, we wanted to see if, let's convert this material itself into a kind of a sensor, right? So this is quite a complex problem. It involves multiple physics. So it involves dynamic loading, fracture, friction, heat transfer, electrostatics, etc. It involves studying this material at multiple scales, because the Psr resistivity that we're talking about originates from nanoscale interactions of carbon nanotubes. It has multiple phases at the microscale, and then eventually the application is at a microscale, right? So So just to briefly to look at what, just to give you an idea of what the material looks like. The material is a composite material at the micro scale. So if you look at the microstructure of the material, it has two phases. It has a granular phase, which is embedded in a polymer binder. These materials are not piezoresistive by themselves, but by adding carbon nanotubes to the polymer binder material, you can make the material inherently piezoresistive. And so just to briefly talk about what piezoresistivity here means, it just means that the resistance and the resistivity of the material changes due to an applied load. So if you can detect what the change in resistance or the resistivity of the materials, maybe you can back calculate or evaluate what the loads applied might have been, right? So you can use that as like a sensing mechanism, and there's a lot of evidence that that these kind of sensing mechanisms do work and are in fact better than your traditional strain gauges or other sensing mechanisms. So to do this, we did both experiments and modeling. But for the modeling part, we wanted to use Peri Dynamics to capture the dynamic response of this material at the micro scale. So we wanted to capture what happens to both the granular phase and polymer binder phase, how the piezoresistivity is manifesting in terms of change of resistance. And we extended the regular elastodynamic Peri Dynamics to an electrostatic version of Peri Dynamics, and we are solving like a coupled system of equations. It's a one-way coupling, but still a coupled set of equations to do this. And so we're looking at this microscale representation and looking at how a compressive wave might under some kind of drop event or some dynamic loading event, how this a compressive wave might travel through this material and activate the piezoresistivity in this material. I have some animations of, let's say, a strain wave going through this material, the potential of in three regions that we're looking at that's changing as the strain wave is going through and as there's damage that's propagating in the material. So as there's damage propagating, there's the material is becoming kind of discontinuous, and it's disrupting the current density that's flowing in the material, and that we can record that change in current density and therefore sense that there's deformation or damage that's happening in the material. There's another look at how the strain wave going through the material and how the conductivity is increasing as the binder material is being compressed, and due to the piezoresistivity of the nanocomposite binder, right, it's becoming more conductive, and we can pick that up using just probes. And we compared qualitatively to what this change in resistance looks like, and found some experimental data where they saw some similar behavior, where there's an initial decrease in resistance or an increase in conductivity. That's the strain sensing phase. And then following that, there's a monotonic increase in resistance. That's the damage sensing phase, right? Because the damage is irreversible, and so there's a monotonic increase in resistance. So these are some of the simulations that we did, and we are I continue to collaborate a little bit with Dr. Seidel and some of his students, and extending this work to not just electrostatics, but also looking at now a three-way coupling between elastodynamics, thermal diffusion, so heat transfer, and also electrostatics. And in fact, some of this work was recently published this month, and there's another paper that's in review based around this work. So what I'm trying to say with these set of slides are there are very specific and very complex problems that need multi-scale and multi-physics solutions with state-of-the-art modeling and numerical methods like Peridynamics, or it could be many other new methods that are being researched. With that, I'll talk a little bit about my current work on Peridynamics. So there are in this couple of slides that David Littlewood from Sandia National Labs uh, put up. There's a lot of ingredients that go into computational Peridynamics. There's a lot of nonlinear constitutive models. There's very computationally intensive contact models. The most common way of solving these equations using a mesh tree method doesn't quite have the convergence properties of, let's say, finite elements. If you're trying to solve these equations implicitly, the tangent stiffness matrices can be very complicated. It can be computationally intensive to evaluate. So the point being, Peridynamics and maybe other niche methods that can have an advantage over traditional finite elements in terms of being able to tackle very challenging problems, but it doesn't come free of charge. It comes at a computational cost, like some of the ones that I listed. And I can give you an example of one of the things that I worked on. So, for example, when you're talking about non-local methods, right? You're talking about a lot of interactions, a lot more interactions between material points or between computational nodes than if you talk about a finite element or a finite difference method. So let's say you go back to that 1D example, right? Let's say you do a simple 1D problem, central difference scheme, and you solve it implicitly, right? You form your stiffness matrix. Your stiffness matrix will have a tridiagonal structure because you have interactions of the node with its neighboring nodes, right? In Peridynamics, you have a lot more of these interactions. So obviously, your bandwidth of your stiffness matrix is going to increase. And when you go to 2 and 3 dimensions, that bandwidth really explodes. I mean, because you're talking about more dimensions, right? So if you increase this interaction region or interaction distance, this bandwidth really goes up. But to model complex problems like propagation of cracks, let's say, you need a large non-local interaction region to get accurate solutions. And you have to deal with this increased bandwidth, which has a computational cost, because now you need more memory to store the additional non-zero terms of the stiffness matrix. It might slow down your solution, things like that. So in the past couple of years, I've worked on some methods to efficiently assemble in 2D, efficiently assemble these tangent stiffness matrix using an OpenMP multi-threaded approach. And that is found to give some pretty good results over, let's say, a conjugate gradient minimization scheme that some people have attempted. A lot of people use a conjugate gradient minimization or adaptive dynamic relaxation method, or some sort of viscous damping or something to get quasi-static solutions using dynamic equations of Peridynamics. But that might take quite a while. So using this method, you can kind of bring down your computational cost and also get pretty good solutions. I won't go into details here. But point being, there's work to be done in this area, and I'm not the only one doing this. There's a lot of great work that's happening in the Peridynamics community. There's also, in Peridynamics, you come across some errors called, they're called surface errors, volume correction errors. which are absent in classical continuum mechanics and finite elements. So again, there are some errors that need to be dealt with, and I worked on this a little bit, and I proposed like an optimization method to reduce some errors in bond-based peridynamic models. So hopefully that will go also towards reducing some of these errors in peridynamic in models. So coming to, I'll just finish up in the next maybe 5 or 10 minutes with some of my thoughts on high performance computing and quantum computing. Less on quantum computing side, because I don't work in that area, but probably more on just general thoughts of high performance computing. So I've thrown a lot of words around in the last 30-40 minutes, HPC, digital twin, Peri Dynamics, a lot of stuff. And some of you might be asking, including me, what is the point of all of this stuff that I've talked about? There's a lot of ways to approach this, but I'll talk about like a specific application or a specific topic, which is the digital twin. So I'll start there. So if you don't know what a digital twin is, I don't know that much about it either, but from my basic knowledge, a digital twin is basically a virtual representation of some kind of physical asset or a process or a system. So for example, this picture shows this really complicated structure of an oil rig. And so a digital twin might be a model or a virtual representation of this physical asset, right? And the connection between those two is using sensors or instrumentation. You take real-time data from the physical world, and you use this in your virtual representation of this thing, and then using this virtual representation, you can get some kind of knowledge or generate some knowledge or insight into the workings of this physical thing, and you can use it to make things better for yourself in the physical world, right? So that's the main idea. So why do we need something like this? So a digital twin can be used to perform hyper-realistic simulations in real time and provide valuable insights into the current state of some asset or process or system. And this idea has been steadily gaining ground, especially in the recent years, especially in the manufacturing sector. And it comes in a variety of flavors, but I mean, it's gaining a lot of importance and gaining a lot of attention in the recent years. In particularly, while I was doing my PhD, I came across this a lot in the context of air and space vehicles, for example. So there's this paper, Glazgen and Stargill, which was presented at AIAA SciTech, and it's like a really well-cited paper, and they describe the digital twin in this way. So they say a digital twin is an integrated multi-physics, multi-scale probabilistic simulation of an as-built vehicle or system that uses the best available physical models, sensor updates, fleet history, etc., to mirror the life of its corresponding twin. So right off the bat, you can tell that multi-physics, multi-scale probabilistic simulation, so modeling and simulation again becomes an essential, unavoidable part of this whole digital twin paradigm, right? There's another paper, really interesting paper called Reengineering Aircraft Structural Life Prediction using a digital twin by a couple of researchers, including Anthony Ingrafia, who's a fracture mechanics expert at Cornell. And they outline the needs of this kind of a paradigm, and they talk about all of these different things that are needed to make this possible. So, multi-scale models, solver technology, adaptive mesh refinement, data analysis, uncertainty quantification, verification and validation. You need like all of these things to come together to make this digital twin paradigm work. And they say, as envisioned, the digital twin of, let's say, a complete airframe will have something on the order of 10 to the 12 degrees of freedom. So that's 1 trillion degrees of freedom. That's like pretty crazy, right? And if multi-scale models of the microstructure are required at even some locations, these models will have on the order of 10 to the 7 degrees of freedom at each location. On top of that, for the digital twin to be useful, and to actually provide the insight that you want, it must execute in real time. So which means if you have a real aircraft flying for an hour, the digital twin must execute that 1 hour of flight time must be simulated in 1 hour of wall time, with all of that complexity, with like 1 trillion degrees of freedom or whatever. So but the first time that I read this, something funny came to my mind. So if you guys have seen the movie Back to the Future, you if you remember this scene where they have to use this time machine that they have built to get back to the future, and they don't have a power source to do this. So they need this, as Doc Emmett Brown says, they need this 1.21 gigawatts of power to make this car, this time machine work, but they just don't have it. And the only solution that they can come up with is to use a bolt of lightning and use that as an energy source to make this work. So when I read this, that's what came to my mind. So do we need to like use a bolt of lightning to supercharge our computers to make this thing work? So its situation is not that bad yet, I would say, because we're making like great advances in supercomputing. So for example, when I was a PhD student, I came across this paper where in 2006, they simulated 320 billion atoms on the Blue Gene supercomputer at Lawrence Livermore National Lab, which is the fastest supercomputer in the world, with a performance of 70.7 teraflops, right? And today in 2020, the Japanese supercomputer Fugaku has a performance of 500 petaflops. So we're more than 3 orders of magnitude higher than we were in just about 14 years back. And rumor is that exascale computing, so performance on the order of 1.5 exaflops, is expected in 2021 at the Oak Ridge National Lab next year. So the acceleration in high performance computing is really quite astounding. So last few slides I have is just on quantum computing, but I'm sure you guys know, or a lot of you know, much more about quantum computing than I do. But just from my reading, there's just a couple of things that I'm pretty excited about. So, for example, in multi-scale modeling and multi-scale materials modeling, we are consistently going to lower length scales to model materials, right? We were doing a lot of molecular dynamics already, but now we want to do a lot more of density functional theory at atomistic scale and lower. And which can be very insightful. They're like first principles. They're about solving Schrodinger's equations and solving for electron densities. But the complexity of solving these increases exponentially with model size. Right now, I think we can do just a couple of electrons or something like that, and we can't go. It's very hard to go higher because of computational difficulties. So apparently, quantum computing holds a lot of promise for these applications. So this will hopefully enable accurate prediction of defects in crystalline materials, processing of polymers, reactions, for modeling reactions in pharmaceuticals. In fact, one of these papers that I came across uses some kind of coupling method where a part of the problem is modeled with is modeled on quantum computers, and the rest is modeled with just DFT on traditional computers, and there's some sort of coupling between these two. So that was really interesting for me to see. Another thing that I'm excited about is there's a lot of interest in doing optimization, solving optimization problems with quantum computing. There's a lot of applications of optimization in social and physical sciences, business and analytics, and even something as simple as least squares fitting of really large data sets can become computationally quite expensive. And there's a lot of work that's being done um, in this area, and some of my work was in least squares fitting and optimization as well when I was doing Peri Dynamics. So I was quite excited to see that as well, and I think I think that's about it. Those are all the slides that I have. It's kind of an abrupt end, but um, yeah, I didn't know how exactly to summarize this uh, talk in just one slide, so I didn't put like a summary slide. But just as in terms of just my thoughts, I hope that I've demonstrated, like gave an overview of what computational mechanics or computational solid mechanics means, to me, and hopefully demonstrated that there's a lot of non-classical, unconventional theories and um, numerical methods that are being employed right now to tackle very challenging problems in science and engineering, but they do come at a high computational cost. So we need new hardware and new software capabilities to implement these new methods and new theories. And both, traditional high performance computing, advances in traditional HPC, and also, maybe in the next decade or next couple of decades, quantum computing, like this whole new paradigm of quantum computing, might come to the rescue of these these problems. So with that, I think I'll stop talking and then hand it over to Abhishek. Mhm. Yeah, absolutely.
Yeah.
Sure. So yeah, that's a good question. So it mainly it is because of its ability to handle discontinuities. So that was I mean I can't speak for the originator of Peri Dynamics, but my impression is that that was the original intention, uh, to like approach this problem of tackling discontinuities, propagating cracks in a completely different way than to try to approach it from your traditional way. So one is that. Secondly, classical continuum mechanics does not employ a length scale into the equation. So if you notice all of these partial differential equations, they can be employed at any scale, all the way from micro scale to the macro scale. It doesn't have an um, explicit length scale associated with the equations. But Peri Dynamics, because you're integrating over a finite region, you're automatically introducing a length scale. And if you're trying to model physics that inherently has a length scale, that might be very useful, right? So if you're trying to model, let's say you're trying to model a fracture process zone at a crack tip, you might want to um, you might want to use that length scale. And in fact, you do it in classical continuum mechanics as well. You have like gradient theories, and you have non-local theories within classical continuum mechanics that were proposed by Ehringen and a lot of his students 20, 30 years back, which use this non-locality to introduce a length scale. So that is another advantage of Peridynamics.
Yeah. Yeah, thank you again for the great talk. So we do have a couple of questions.
Sure.
So the first question is when you started talking about the nuclear fuel, and somebody asked, could you explain more on the fracture of oxidized nuclear fuel?
Sure. Yeah. So I haven't personally worked on that, so I can't go into a lot of detail. But basically, oxide nuclear fuels, just a type of nuclear fuels. There's metallic nuclear fuels. There's oxide nuclear fuels, nitride fuels. There's a lot of different type of nuclear fuels. But because of the extreme conditions under which this material operates, you have like very high gradients of temperature, right? They the spatial There's a high spatial gradient of temperature, and so it this material expands very non-uniformly, and I think it expands a lot in the center along the axis of the fuel, and not as much on the outside. So this sets up a lot of stress gradients, and that causes fracture in the fuel. And I think in oxide nuclear fuels, they do fracture in more of a brittle manner than in metallic nuclear fuels, where there's a lot of creep and plasticity involved um, in the fracture process. So I hope that answered the question.
Yes. um, Thank you. Yeah, that was a very good answer for this. Also, another question is, I guess, let me go with this one. Is Peridynamics a Lagrangian method or an Eulerian method?
It's a great question. Um, uh, Originally, it was proposed as a Lagrangian method. Um, like most papers, most of the people that use peridynamics do it for solid mechanics purposes, and they do it in a Lagrangian way. But there are Eulerian forms of peridynamics that have been proposed, and in fact, it has been used for modeling of fluid flow as well. So there are both flavors of Lagrangian and Eulerian.
Oh, I see. Um, oh, and also, is Peridynamics able to simulate any singularity that arises in PDEs?
So, Peridynamics, I should say that it's not just a numerical method. It's not just a different numerical method like you would say finite element is a numerical method to solve partial differential equations of classical continuum. It's a different theory all by itself, right? Because
Right.
you are expressing the internal forces in a different way. So, firstly, you don't come across partial differential equations in peridynamics. You're dealing with integral differential equations where the differential part comes from the time derivative, not the spatial derivative.
Right.
Secondly, uh, so the point is that you are able to um, simulate a singularity in some sense. Sorry, the network kind of disconnected.
Yeah. So,
So anyway, the short answer is you're not exactly dealing with singularities, but you can model uh, discontinuities. And on that note, I would also like to mention that there's also finite element methods to solve the equations of peridynamics.
oh, I see. So it's not necessarily just the numerical algorithm or
No,
numerical method. Okay,
no. So
it's essentially looking at it from a different point of view.
yeah, and you can solve peridynamics with like Galerkin weak formulation, with a finite element type of
Right.
thing, and you can do finite difference or many like a different methods to do
Okay. Great.
peridynamics. Yeah.
Um, this question is, I guess, kind of as a whole, how can we use high performance computing for multiphysics?
Um, I'm not sure what exactly you mean by how it can be used, but we are already using high
Right,
performance
right.
computing for multiphysics, right? I mean, um, if you're using just just proprietary software like Abacus or ANSYS to do some kind of, let's say, fluid structure interaction or any kind of problem, and let's say even if you're running it on like a simple workstation with like 8 cores or 16 cores, you could say that you are doing multiphysics for using a high performance computer, right? You're solving coupled equations in on multiple threads in parallel. So you are already doing it, and yeah,
Right.
that's what
I
we
think
do.
like maybe if you could reiterate the complexities, specifically, let's say for structure mechanics, and then I guess we can say from our end of how for like CFD to kind of get kind of take that point as well. But from your end, can you describe a little bit again a little bit about the complexities and essentially why we would need, let's say, high performance computing and why over let's say desktop or laptop are unable to solve those
Right,
equations.
right. So, yeah, so in that sense, for example, the problem that I talked about, we are doing micro scale simulations, and we are doing just like proof of concept almost kind of simulations, right?
Right.
And to really tackle like that problem, it really has to be multi-scale, where you're looking at the nanoscale, micro scale, and uh, move that up to the macro scale. And so you're looking at complexity across different scales, but you're also incorporating a lot of multiphysics. Like, for example, you're talking about dynamics of the material, you're talking about frictional, let's say, heat generation, and then heat transfer, how that heat generation affects the Psr resistivity. So a lot of these coupled phenomena, um, and coupled phenomena at different scales. So
Right.
you're just to keep adding complexity to the problem, but at the same time, again, you need like more computing to solve these challenging problems.
Right.
So
Right.
in that sense, we don't need like more powerful computers for the problem that I talked about, or any other complex problem that many of you maybe work on.
Mhm. Yeah, and I can shed a little bit light on the computational fluid dynamics, which is one portion of multi-physics simulation. So in that, I can give you like a perfect example of being anything realistic. So what I currently work on is on hypersonic flows. So in there, we are dealing with scales, similar scales that Dr. Prakash talked about, in terms of we're dealing with scales on the micro level all the way up to, let's say, a meter level. So when we talk about those scales, we're talking about they're called eddies, but essentially they have they're essentially nothing but small vortex that are occurring in the flow. And right now I'm talking about turbulent flow, which is very chaotic, unpredictable, and to resolve everything in that sense, because of the wide variety of the time scale, of the length scale, as well as you're working with time scale as well, because we're working from nanoscale all the way to millisecond to seconds when we talk about in hypersonic flows. So in that sense, the number, so for us, what we do is you can think in terms of the floating point operations, or flops. And the number of floating point operations can go up to power of like 30, 40. So in order to do that, our computer, let's say with a I think one core processor, it would take thousands of years to solve. So that is the need. That is why we have the need for the high performance computing. And even so, with high performance computing, some of these complex problems take just way too long. Like we have a really nice example where one of the problems done by a research group, which I think Abhishek might be involved in, but they essentially use one of the national lab computers to do that. And for the whole simulation itself took several months. And then to resolve the whole solution, it takes several months to do that. And on top of that, some of these problems are unachievable right now, just because we don't have the computing power. So they're just unattainable, not because of physics point of view, or not being able to understand the physics, but it's just that we don't have enough computational power, even with the high performance computing. So I guess that's a nice lead up into why the next wave of future is definitely build larger and larger supercomputers, but there's going to be some kind of a limitation on how large supercomputers can be. So then the next the paradigm shift that needs to occur is towards quantum computing, and which is what we're trying to target at Boson QSI. Um, okay, so another question is let's see. Okay. What is the difference between peridynamics and continuum mechanics, and how does it involve finite element analysis? FEA.
Okay, so let me let me clarify a couple of things. So continuum mechanics is a general term which says you're talking about things that are continuous. So that's what just continuum mechanics means. So I wouldn't say there's a difference between peridynamics and continuum mechanics, but there's a difference between peridynamics and classical continuum mechanics, right? Because classical continuum mechanics comes with a certain set of assumptions of locality, and if you go through like your derivations of the Barron's laws, the reason that they are partial differential equations is because of the assumption of that locality. So peridynamics is also a continuum theory, but it also assumes a continuum media. There's an infinite amount of particles, and every particle is infinitesimal in size. So it's also a continuum theory, but just that the interactions between particles are, it is hypothesized that the interactions between particles are different. So in that sense, the main difference between peridynamics and classical continuum mechanics is how the interactions between particles are different. So that's my answer to the first part of the question. Second part of the question, how it involves finite element analysis, is the theory itself does not involve any finite element analysis. Like I mentioned, finite elements, finite difference, finite volume methods, these are numerical methods to get an approximate solution to your field equations, not exact solutions. They are methods, they are numerical methods to get approximate solutions for your field equations. And they could be, classical continuum mechanics equations, or they could be peridynamics equations. So I hope that clarifies your question.
Yes, I think that was a really well answered. I think one of the last questions is, can you please explain what would be the maximum range between particles or discontinuities that peridynamics can describe?
Yeah, that's a great question. There are no like rules in the theoretical sense. Let me put it that way. In the theoretical sense, there's no rules for what this interaction distance could be. So one, in a practical sense, when we're using peridynamics as a tool for modeling fracture, modeling problems of fracture, there are some general guidelines where you discretize the model enough to get like a good representation of the fracture pattern. So if you would do like a convergence study, like you would do with finite elements, and see if your crack paths are converging, and generally you would take your. It's been observed that let's say you have a uniform grid of particles, like you would have in like a finite difference method for CFD. You have a uniform grid of materials. Generally, to get good fracture patterns, you would target between 3 to 4 times the lattice spacing as your interaction distance, as a general rule. But in a more in a more theoretical sense, you would try to tie that interaction distance to some kind of length scale of the physical phenomenon that you're describing. So some of the work that I did during my PhD, we were doing peridynamics modeling of electron hopping mechanisms between carbon nanotubes, which is the source of Psr resistivity in carbon nanotubes. So to model that, we set the interaction distance to the maximum distance between carbon nanotubes in which, below which electron hopping takes place. So that was a way to actually bring in some physical length scale that has some physical meaning into this theory of peridynamics, or into the model of peridynamics. So there's like two kind of answers to this question, and I hope I answered your question.
Yeah, yeah. Well, talking about the, I guess, FEA a little bit, can you tell what's best source to grasp a deeper understanding on computational solid mechanics?
So there's a lot of good there's a lot of good books out there. So, for example, to get a good grasp of the basics or fundamentals of continuum mechanics or solid mechanics would be these books by um, Holzapfel, Alan Bauer, J.N. Reddy, um, Malvern. There's a lot of good books for learning the theoretical basics of continuum mechanics. But as a general rule, I would say, like, the example that I give, like a 1D example that I give. So it would be good, like it would be very educational for you for anyone interested to just start with like let's say a 1D problem, right? And then use that as a starting point and try to discretize that using, let's say, finite element method, using a finite difference method, a finite element method, or a finite volume method, and just try to get a solution with a couple of these different types of method. And that would give you a really strong understanding of how these methods work.
Right, right. Okay. And also the question had same for CFD. So what I would say for CFD is first, and I think Dr. Prakash can also agree with me on this, is you need to have a good understanding of the theoretical. So I would say for solid mechanics, you would need to know the theoretical background before you would try to kind of simulate or model. Same with CFD, you would need to have a really good understanding of how fluid mechanics works. No, not necessarily just remember the formulas or anything, but actually get a good understanding of all the different things that can occur in fluid mechanics before you kind of move to modeling fluid dynamics, which is CFD. And for CFD itself, there are many great books by Dr. John Anderson. If you are from mechanical or aerospace engineering, you've heard of Dr. Anderson because he has written many, many great books in this regard. Also, you could also look at Dr. McCormack from Stanford University. He has a great book on CFD, and there are also several books by Hirsch, Hirsch. I think the Hirsch has like two different volumes of internal flows as well as external flows, CFD of internal and external flows. So those are definitely great tools. You can begin by getting understanding the theoretical knowledge of computational fluids before even applying it. But yeah, that's a really great tool to start, and of course you can Google many more things regarding that. I think the last question is let's see. So somebody asked, I think this is more of a clarification question. So essentially, Peridynamics involves solving governing equations as integral with non-local influence instead of solving them in partial differential form with local influence. And what he means by that is in the classical low order solution for PDEs using intermediate neighbors.
Yeah, that's a really good way of putting it. Yeah, I couldn't have put it better myself. So that's essentially what it is in a nutshell. Is you're writing your governing differential equations in a slightly different form. I mean, it's not necessary that the classical continuum mechanics way is the only way to do things.
Right.
Right. So this is a hypothesis. I mean, this is a theory also, and there's a lot of validation that's been done, and that's validation that's been ongoing.
Right.
So, yeah.
Okay. Yeah, we can conclude the Q&A session as well. Thank you again, Dr. Prakash. I just want to remark that people loved your talk, that several people also asked if you can conduct any workshops on Peri Dynamics.
Oh, wow. That's think about. Yeah, thank you. Think about. Yeah, thank you so much for your comments.
Yeah, thank you, Dr.